Hello, and thank you very much for your interest in this presentation. My name is William Giare, and I'm a postdoc at the University of Hawaii. Today, I would like to discuss about the latest DESI results, and in particular about their preference for dynamical dark energy. I will review a few aspects surrounding the robustness of this preference, and then I will try to relate these results to cosmological tensions. In particular, I will focus on the Hubble tension, and I will try to answer a very simple yet important question. Assuming that both DESI and the Hubble tension are genuine hints of new physics beyond lambda CDM, is it possible that they are two different manifestations of the same underlying physics? Or do we need two different ingredients to explain these two anomalies? Let me start from what actually DESI measured. DESI provides us with very precise measurements of the parallel and perpendicular BO distance. In practice, DESI is measuring cosmological distances at different redshifts relative to the value of the sun horizon. All the quantities measured by DESI are proportional, therefore, to the integral of 1 over the expansion rate of the universe or 1 over the expansion rate of the universe itself. Now, in a lambda CDM cosmology, the expansion rate of the universe in the redshift range plotted by DESI, which is between 0 and 3, takes a very easy form. Essentially, it is controlled by two parameters, H naught and omega matter. H naught is the present-day expansion rate of the universe. It is well measured by cosmic microwave background observations. In particular, the Planck CMB data measure a value of H naught around 67.5 plus minus 0.5 kilometer per second per megaparsec once we assume a lambda CDM model of cosmology. However, the same parameter can also be measured through distance ladder methodologies, such as using type 1a supernovae as done by the Schultz collaboration. And they get values of H naught that are around 73 plus minus 1 kilometer per second per megaparsec. Now, you know that these two numbers are in disagreement at the level of 5 standard deviations. And you also see that many other estimates of the Hubble parameter based on early universe measurements that rely on a lambda CDM cosmology are in quite significant disagreements, not only with the value provided us by Schultz, but with a multitude of other local universe estimates of the Hubble parameter that are scattered around the value measured by Schultz. Therefore, it looks like there is a gap in our understanding of the early universe and the local universe, and this is the reason why many have said that the Hubble tension may be pointing to the physics beyond the standard lambda CDM model of cosmology. Now, the DESI results added new information in this puzzle because while the DESI biomeasurements can be well explained in a lambda CDM cosmology, if we look at the best fit lambda CDM cosmology resulting from DESI, we find that is in mild 2.3 sigma disagreement with the best fit lambda CDM cosmology emerging from Planck. And in particular, DESI favors larger values of H naught and above all, smaller values of omega matter compared to Planck CMB data. Now, you see that this mild disagreement between Planck and DESI is mostly driven by this mismatch in the value of the matter density parameter. And in my opinion, this is quite interesting because suppose that the universe is not exactly lambda CDM at low redshift. Suppose that there is some new physics beyond lambda CDM and DESI is capturing this new physics. If we enforce this data to be explained within a lambda CDM cosmology, any new physics can emerge only as a mismatch in the value of omega matter and the Hubble parameter, simply because these are the only two parameters that controls the theoretical predictions for the quantities measured by DESI in a flat lambda CDM cosmology. For this reason, in my opinion, it's important to question whether these mild disagreements may be pointing to new physics in the late universe. And in particular, I will say that in the redshift range proved by DESI, the most important assumption is assuming that the dark energy sector of the cosmological model is well described by a cosmological constant. The first thing we can test, therefore, and this is exactly what has been tested by the DESI collaboration, is what happens if we relax this assumption and we consider a generic dark energy component with a generic equation of state W that can in principle evolve with the redshift. What the DESI collaboration has done is to consider this precise analytical form to describe the evolution of the dark energy question state. This is known as CPL parameterization. The CPL parameterization is a linear parameterization in the scale factor A. It consists of two free parameters, W0, which is the present day value of the question state, and WA, which is the parameter that controls the evolution of the question state with the scale factor. You see that within the CPL parameterization, you can always recover a cosmological constant when W0 is -1 and WA is equal to 0. This corresponds to this point in the parameter space. However, you also see that combining DESI BO data with CMB and type 1a supernovae, different combinations of data consistently favor a region of the parameter space that excludes a cosmological constant and gives a preference for dynamical dark energy models at the level of 3.5 standard deviations. Now, I want to spend a few words to assess the robustness of these results, and in particular, I want to start from a very simple question. Is it possible that this preference is somehow biased by assuming a linear CPL parameterization to describe the evolution of the question state? In particular, assuming the CPL parameterization, we observe a very peculiar behavior of the equation state. We observe an equation state that is quintessence in the present epoch, but that was phantom in the past. And the quintessence to phantom crossing happens at redshift around 0.3, 0.4. The question is whether and to what extent this behavior is biased by assuming a linear parameterization of the equation state. We tried to answer this question in this paper here, and we essentially analyzed a multitude of alternative dynamical dark energy parameterizations. These parameterizations, just like the CPL model, have two free parameters, W0 and WA, but unlike the CPL model, in these alternative parameterizations, we can deviate from the linear regime either at low redshift or at higher redshift. And what we observe is a remarkable consistency across all these models that we analyzed. We always find a preference for a present-day quintessence equation state and an equation state that was phantom in the past. And most importantly, this quintessence to phantom crossing always happens more or less at the same redshift. Therefore, we concluded that this behavior of the equation state is not intrinsically biased by assuming a linear parameterization, but it seems to be a more general preference coming from observations themselves. That said, I want now to answer a different question, namely, is this preference for dynamical dark energy coming only from the DESI biodata, or is it supported by other observations? In this review paper, we analyzed 35 independent combinations of data, and in particular, we quantified the preference for dynamical dark energy across all these combinations of data. And what we find is that the preference for dynamical dark energy is not coming just from the DESI BO measurements. Actually, if we consider different combination of BAO and type 1a supernovae, we already observe a preference for dynamical dark energy with a behavior that is very similar to what is found in DESI when we consider the old BO measurements from the SDSS collaboration. You see in these panels here that combining SDSS BO with Phantom Plus, Union 3, and this year 5 supernovae, we already see a mild preference for dynamical dark energy with an equational state that was quintessence in the present and phantom in the past. Of course, when we replace SDSS BO with DESI, this preference gets stronger. In the bottom panel, you see the same behavior, adding to the analysis CMB data from Planck. In particular, you see that combining CMB, BO from SDSS, and different type 1a supernovae, we already see a preference for dynamical dark energy, even in absence of DESI BO measurement. One more time, when we replace SDSS BO with DESI, this preference becomes much stronger, but it was there also without CMB DESI, without BO from DESI. This is telling us three important things, in my opinion. First of all, that this preference is not just coming from DESI BO. It is supported by different type 1a supernovae, and also it's supported by CMB data. And in particular, in this paper of mine, I have identified the subset of Planck CMB data that strengthen the preference for dynamical dark energy. I found that this preference is strengthened by in-mode polarization measurements in large angular scales. In particular, the Luel EE Planck likelihood is strengthening the preference for dynamical dark energy. If we look at CMB experiments other than Planck, we still observe a preference for dynamical dark energy, but it is reduced compared to Planck. And the reason is that Planck is the only CMB experiment that is currently measuring in-mode polarization at such large angular scales. Okay, I hope this clarifies a little bit where the preference for dynamical dark energy is coming from. Now I want to address a different question, namely, is dynamical dark energy able to solve the Hubble tension? Here the answer is no, dynamical dark energy is not able to solve the Hubble tension. You can see this clearly from this plot here. In red, you see the constraints that we obtain in a lambda CDM cosmology, while in green, you see the constraints we obtain in a dynamical dark energy cosmology. In lambda CDM, we measure values of H naught around 68, 67, 68. And you see that assuming instead dynamical dark energy, these results are shifted towards smaller values of the Hubble parameter. This is already telling us that dynamical dark energy is not good to solve the Hubble tension. And you can see this even more clearly in these two-dimensional probability contours. Again, in red, you observe the probability contours in lambda CDM. In green, you observe the probability contours in dynamical dark energy. If you want to solve the Hubble tension, you should move along these directions that labeled as shoes, but you see that the green contours shift in a direction that is either opposite or perpendicular with respect to where you would like to move to solve the Hubble tension. So unfortunately, this model is not able to address the Hubble tension. It's able to provide a very good explanation to the DESI biomeasurement, but it's not good to solve the Hubble tension. The question then becomes whether is there a model that can explain DESI baryon acoustic oscillation measurements and at the same time solve the Hubble tension. A first good step in this direction is provided by models such as interacting dark energy. In interacting dark energy cosmology, we assume that there is an interaction between dark matter and dark energy, and in particular that there is an energy momentum flow between the dark sector components. Assuming an energy momentum flow from dark matter to dark energy, we obtain a phenomenology which is somehow similar to dynamical dark energy. So we are able to explain baryon acoustic oscillation measurements from DESI better than lambda CDM. And at the same time, we obtain values of H naughts that are in much better agreement with shoes. Therefore, we are able to reduce the Hubble tension down to sigma. However, while these models can explain the SEBO better than the CDM and move H naught in the right direction, it seems by now established that this kind of late time solutions to the Hubble tension cannot alone fully resolve the Hubble tension. These points can be seen very clearly. I don't have time to discuss this now, but I leave this open for the discussion section. What I want to say is that it seems by now established that a full resolution of the Hubble tension should also involve new physics before recombination. And in particular, the overall philosophy of early time solutions is to introduce new physics prior to recombination to decrease the value of the sound horizon in order to increase the value of H naught. The reason is that if we decrease the value of the sound horizon, in order to preserve the value of the angular scale of the horizon that is extremely well measured by CMB data, we also need to decrease the value of the angular diameter distance. And a simple way to decrease the value of the angular diameter distance is to increase the value of the Hubble parameter. You can see this clearly in this plot. In lambda CDM, we are here. We measure the sound horizon to be 147 megaparsec. If we decrease the sound horizon, we move along this gray band. We obtain larger values of H naught, and eventually we will be in agreement with shoes. This requires a reduction in the sound horizon of about 5–10%. The question then becomes, how can we reduce the value of the sound horizon? Well, if we look at its definition, we observe that the sound horizon is defined as the integral between soon after inflection and, say, recombination of the baryon photon sound speed divided by the expansion rate of the universe. Therefore, a very easy way to reduce the value of the sound horizon is to increase the expansion rate of the universe before recombination. And models that can increase the expansion rate of the universe before recombination and to decrease the sound horizon are quite discussed in the literature. One example is early dark energy. In early dark energy cosmology, we have an additional degree of freedom, perhaps a scalar field, that becomes relevant just before recombination, increasing the expansion rate of the universe before recombination, decreasing the sound horizon, and possibly increasing the Hubble parameter. While there is no intrinsic preference for early dark energy in CMB data, these models are successful in solving the Hubble tension when we impose a shoes prior on the Hubble parameter. Now, the situation is therefore more or less the following one. It looks like if we want to go in the direction of solving the Hubble tension and explain this, we need something like interacting dark energy. But if we want to fully resolve the Hubble tension, perhaps we need something like early dark energy. At first sight, these look like two different ingredients that we need to introduce, one in the early universe, one in the late universe, two different new physics, two different ingredients. The question I'm working on right now is the following one. Is it possible that these early time modifications and late time modifications are just two different manifestations of the same underlying dynamics? In other words, is it possible to find a unified models of early dark energy and late time interacting or dynamical dark energy? Well, this work is still in preparation, but what I can tell you is that in order to achieve a successful unified scenario where you get an early phase of dark energy that can solve the Hubble tension and a late time phase of dark energy that can explain DESI biomeasurements, is quite non-trivial because the scalar field must pass through a multitude of dynamical phases that require a very specific dynamical structure and therefore a quite non-trivial potential. And in particular, in this work that is currently in preparation, we are trying to characterize all the requirements that we need to achieve this possible unified scenario where you can simultaneously have an early phase of dark energy and a late phase of dynamical or interacting dark energy that can simultaneously explain the Hubble tension and DESI biomeasurements. Let me now come to my conclusions. My conclusions are that this is a quite interesting time because the DESI data seems to challenge the lambda CDM cosmology, pointing to new physics in the dark energy sector. A very simple interpretation is provided by dynamical dark energy scenarios. These are robust against different dark energy parameterizations, against different combinations of data, but dynamical dark energy scenarios cannot solve the Hubble tension. The question is then, is there a model that can simultaneously explain the DESI biomeasurements and solve the Hubble tension? A first step in the right direction is provided by interacting dark energy models. This can mimic dynamical dark energy and explain DESI while also reducing the Hubble tension down to sigma. However, a full resolution of the Hubble tension likely requires new physics before recombination, such as early dark energy, and finding a unified model that can give you simultaneously such an early phase of dark energy and a late time phase of interacting or dynamical dark energy is quite non-trivial, but perhaps possible under some conditions, specific conditions on the dynamics. This is everything from my side. Thank you very much for your attention.